All right. So when it comes to the natural logarithmic function, it's built on the natural base e, right? And e is a specific special number. It's a special number which is equal to 2.71828828459045 specific. And so, for example, let's suppose I've got y equals to 2 to the power of x. This function, if x is equal to 0, it'll go through 1. And if x is less than 0, it will start decreasing, getting closer and closer to 0. And as it increases after 0, it will go exponentially up. That's y equals to 2 to the power of x. It's a specific value over there. Now, the function e is very much similar to that as an exponential function. But as it increases, it will also do that, but this will be y equals 2.71 to the power of x. It'll also go through the number 1, because when x is 0, anything to the power of 0 is 1. And it'll look very similar to that, except it's 2.71828, a specific number. So instead of writing a number out, we write y equals e to the power of x, which is an exponential function. And we call it the natural logarithmic function of that. Now, the most amazing thing about this is that when you derive this function, so if y is equal to e to the power of x, and you derive this function, it stays exactly the same. What does it mean? That means that if I have to find the gradient, for example, at, let's say, x equals to 2, all right? If I put x equals to 2 into this function here, it'll become e to the power of 2, which is going to be my y value. So what are we implying? We're implying that the gradient at every single point on this curve is the y value. Whereas the gradient of this function is different. I mean, if you have to calculate the gradient of this function, it's not going to be exactly the same. We also have to remember that with the power rule, if you got y equals e to the power of 2x, then when you derive that, you're going to multiply it by the gradient or the derivative of 2x, which is 2e, but you keep the original function the same. So here we just have an amplitude change if we had that function in place. So y equals 2 e to the 2x would be derived to become that. Y equals e to the power of 4x would become 4e to the power of x, e to the power of 4x. And we keep the original function exactly the same. Y equals e to the power of x squared would become 2x e to the power of x squared, keeping the original function the same, but deriving the power and multiplying it. Okay, so in a nutshell, that's basically what that is. All right, so now let's look at logs now, right? The natural logarithmic function. Now, firstly, we know that if we've got logs, what does log of e represent? What is the log of e represent? So the power is raised to get a specific number. So for example, let's say the logarithmic base 10 is 3, right? Logarithmic base 10 is 3. We know that if I go log of 1,000, that's going to be the same as log of 10 to the power of 3, which is the same as 3 log 10. So, a bit of log rules here. And at the same time, we know that the logarithmic function of base a x, which is equal to y, is the equivalent to x equals a to the power of y. So natural logarithms, okay, are logarithmic functions which have base equal to e. So natural logarithmics are generated representing log base e of x equals to y, which becomes the equivalent of this case, it'll become x equals e to the y. All right, does that make sense? Or the other way around? Yeah. So let's just show you. Let me just show you how that works for the first part. Remember, if you've got log base ax equals to y, and you make this into log x divided by log a equals y, and then move that across and multiply it, you get log x equals y log a, and then move the power to the top, becomes log x equals log a to the power of y, and then drop the logs, leaving with x equals a to the power of y, and that's how we end up there. And we repeat the same process over here. With these y and x values, I mean, let's say we have to change it into log e a equals b. It could also then obviously mean that a equals e to the power of b. Alright. Now, if you have y equals log base e of x, they've replaced that with y equals log x, but instead of writing log x, they write ln, or natural logarithmic. So what we're saying is that ln is the equivalent of log base e. Instead of writing log base e every single time, you write ln x. Okay? And that's the conversion to that. And that's what you'll see on your calculator. And it implies that there's a hidden base e over there, which we need to use. Alright, let's go to the next thing. If I've got log base e of e, that's going to equal 1, right? Because log a of a is equal to 1. But we just stated that the base e can be replaced with ln. So therefore ln e must equal 1. Alright? And that's one of the properties of the is that ln e equals 1, or log, you can also call it log e, some people call it ln, but it's a natural logarithmic of e, which is equal to 1. And then the same properties of logs apply. So if you've got log of xy, you can use a product log x plus log y. Division rules apply. Log x over y will equal ln x minus ln y. I'm just going to use ln. And also the power rule applies. So ln x to the power of y. Power goes in front, becomes y ln x. And the one thing also we must remember is the derivative of ln x is given by, so if y is equal to ln x, then the derivative or the slope of this will be given by 1 over x. The first order derivative of this natural logarithmic function is equal to the reciprocal of that function. Okay, so the reciprocal of that function is the derivative. Okay. When you find the log of any number that's less than 0, it's undefined as well. If you find ln of a number that is less than 0, then it will be undefined. So it has to be 0 or more. This has to be greater than or equal to 0. Well, if you have to calculate ln of 0, right, that also won't work. So not equal to 0, just greater than 0. Okay. Remember, you're dealing with an exponential function. It doesn't actually reach the x-axis as well. So here we go. So that's going to be greater than 0. The next thing is we've got ln of 1 is equal to 0. Okay, And how do we solve that? Remember, ln of 1 implies log base e of 1, which implies log base e of 0, which means power rule 0 log base e implies 0 times 1, which implies 0. And that's how we go back there. Okay, so log of 1 is equal to 0. If you find natural log of infinity, it will become infinity. And if you find the natural log of -1, we call that I, which is Euler's constant. We know it doesn't exist, but it does exist in Euler calculations as well. So let's put all these properties of the natural logarithm on one page. Properties of natural logs. Let's see if we can fit on one page. Alright, so we know that ln xy equals ln x plus ln y. Ln x divided by y equals ln x minus ln y. Ln x to the power of y equals y ln x. If y equals ln x, the derivative is equal to 1 over x. And the next property is that if you find the ln of x and x is less than 0, then it will be undefined. We also know that ln of 1 is equal to 0, ln of infinity is equal to infinity, and ln of -1 is equal to I, which is Euler's constant. Alright, so there's some properties over there of logs. Another one was ln of e equals 1. Alright, so if I have ln of e to the power of x, then that's going to be equal to x, right? Because that would imply x ln e, which will be 1, which will be x. Alright, so there's another two more properties over there. Properties of natural logs. Let's look at an example now. So question 1, we asked to evaluate the value. So find the value of natural log of the square root of e. What is ln root e? Well, that's ln e to the power of half, which will be half ln e. And you'll be implying we're using the power rule. And then e is equal to 1. So half multiplied by 1, which is equal to half. Let's do another question. Question number 2. We asked to evaluate ln square root of x minus 1 over e. So I can rewrite this. I can say ln of the square root of x minus 1 over e is equal to ln x minus 1 to the power of half over e. And so that will equal a half ln, well, I have to distribute it, right? So I'll distribute it using the quotient rule. X minus 1 half subtract ln e. And it becomes a half ln x minus 1 to the power of negative a half. Alright, just double check that now. So power rule, do we even subtract it? Am I deriving it? No. Right, so we're just moving the power to the front. and multiplying it. Do we minus 1 from it like a derivative? Or not? It seems like we should, but we don't. Okay, so we keep that half, moving the whole half and leaving that empty. Okay, so this is going to be minus then e, which we know is 1. Okay, because the logarithm is 1. And then from that, I've got this function now, which is half ln x minus 1 minus 1. Can I do anything else after this? All done. All right, so here we use the quotient rule to get there. And then here we use the power rule to get there. And then we're done. We stop here.